So section 2, exercise 1, we have 5 vertices and we need to connect them in ways that all these conditions are met. So the first condition is that the vertex 1 has degree 3, it means first vertex must have 3 edges. Second condition, V2 is odd vertex, that means the vertex has odd amount of edges. V3 also, degree 2 means 2 edges, V4 and V5 are adjacent, that they must be connected by an edge. So let's start building. I've already built it and we can check all the conditions that. So let's start with the first vertex. It has to have 3 edges, so we can see V1 is connected with V2 and V5, so the first condition is exist. So next condition, let's take the V3, it has to have 2 degree, so we can see V3 connects with V4 and V1, so this condition also exists. Next condition, V4 and V5 has to be adjacent, so they are already adjacent because they must be connected by an edge. And also the last condition, that V2 is an odd vertex, we can see that there is only one edge, 1 is an odd number, so all the conditions are met and all conditions are satisfied, and this is the final graph. Section 2, exercise 3, we have to draw a graph by the following conditions, that every vertex is adjacent to 2 vertices, that means every vertex has degree 2. And next condition is that every edge is adjacent to 2 edges. This means that each edge shares a vertex with exactly 2 other edges. So no one edge is isolated. So by this condition we can consider that this is a cycle graph, and here is the answer. So we have to check the all conditions. That first condition, that every edge has 2 degree. So for example, for the first vertex we can see that it has 2 degree. First it's from V1 to V2, and next that it has 2 edges also for V2, V3 and V4. And also for the next conditions, that every edge is adjacent, we also can see that, for example, this V4 and V3 edge has adjacent to the V1 before and V2 and V3, so we can show that this graph is follow all our condition. Section 1, exercise 5, we have to draw a graph with 5 vertices and as many edges as possible, and we have to answer to the questions, which is how many edges does our graph contain and what is the name of this graph. So let's answer to the second question, the name of our graph, and our graph is complete graph because as many edges as possible means that every pair of vertices is connected by an edge. So in other words, every vertex is adjacent to all other. So next question, how many edges does our graph contain? So we can use this formula, the degree of all vertices equal to 2 multiplying 2 edges. So by substituting our information data, 5 multiplying to 4, 5 is all vertices and 4 is the edges which has each vertex. So and final answer is 10, so we can claim that we have 10 edges. And also our final graph looks like this, and we can check all conditions that so we can see that it's complete graph because one graph is connected with each other. For example, first vertex is connected with second, third, fourth and fifth graph. So this is the final answer.
We are given a graph with 12 verticals and 28 edges. By the hijacking lemma, the sum of all degrees must be 2 times 28, which is 56. Part A, degree 3 or 4. Let x be the number of degree 3 verticals and y be the number of degree 4 verticals. We got 2 equations, x plus y equals 12 and 3x plus 4y equals 56. From the first equation we know x equals 12 minus y. Now substitute into the second equation 3 times 12 minus y plus 4y equals 56. That is 36 minus 3y plus 4 equals 56, which simplified to 36 plus y equals 56. So y equals 20 and x equals negative 8, which is not possible because we can't have a negative number of verticals. And part B, degrees 3 or 6. Let x be the number of degree 3 verticals and y be the number of degree 6 verticals. X plus y equals 12 and 3x plus 6y equals 56. Substitute x equals 12 minus y into the second. 3 times 12 minus y plus 6 equals 56. That gives 36 minus 3y plus 6, y equals 56. So 36 plus 3y equals 56, which means 3y equals 20, and so y equals 20 divided by 3, which is not a whole number. So to conclude, in both cases, it's impossible to create a graph with these conditions. The model on the left is of the graph G, A, B, C, D, AB, BC, AD, and DA. And the model on the right is of the graph G, A, B, C, D, A, and also AB, BC, CD, and DA. So it's a subgraph. And B part, the graph G depicted on the left has two verticals of degree 3, but the graph H depicted on the right only has one vertex of degree 3, hence G is not subgraph of H. C part, the left graph is bipartite graph. Two verticals are connected to three others. So in the right graph we can find 5 verticals and match them so that 2 are connected to the other 3 in the same way, and all 6 recurrent edges are there. So it's a subgraph. And D parts. The left graph has 5 node paths with an extra node connected to both ends. In the right graph, some of these extra connections are missing, so the left graph is not a subgraph.
Hi, I'm going to explain how I solved task 70 and 80 from the graph theory worksheet. Okay, first, task 70A, degrees of verticals. I was given a graph, which 3 verticals, V1, V2, V3, and I need to find the degree of each vertex. I use 2 rules, a loop, and H that connects a vertex to itself, it counts as 2, and a regular edge between 2 verticals adds 2 and to each vertex. So, first picture, V1 connects to V2, and we have a loop. Overall, we sum connect and vertex, and we connect, we have 3. And by the way, we have 2 vertex, and it counts as 2 plus 2 equals 4. Its total degree is 4 and 3 because only one vertex, because therefore degrees of V4 equals 2. Okay, now we go to D. Can degrees 1, 2, 3, 4 exist in graph with 4 verticals? Firstly, we sum of degrees, but sum of degrees is over and even. Where we sum this is equal 10 even. But on vertex has degree 4, and that is impossible in a 4 vertex graph. The maximum degree is 3 because of vertex connects to 3 others. And therefore such graph cannot exist. And what's next? 18a. We need to know exists this graph or not. Okay, first thing, we need to sum rails of graphs. Even if it's old, it's not exist. How is first example, not exist. We have 70 and it's old but not exist. Secondly, B, we have sum from 1 to 100 is 5050, but instead of 1, replace 3, 2, and we get 5050 minus 1 plus 6 is equal 155. It's also odds, therefore it can't exist. C, 5 plus 5, we have some 20. Even have use Hakimi Heaven's algorithm, we have remove 5, we get 5, 4, 3, 2, 1, only 2, and into each value we minus 1. We have 4, 3, 2, 1, remove 4 and minus 4 values. We remove 4 and at least minus 1 to each 4 values. We have 2, 1, 0, minus 0. If we got minus 1 on the graph, it means the graph is not exist. Okay, this we have in the same algorithm. It's even. We have 6 pivots. It's even, and we can connect to 3 pairs. How I picture it. The rest because exist. 5, 4, 3, 2, 1 is odd, not exist. 5, 3, 2, 1 is even. Use Hakimi algorithm. Remove 5 and minus 5 values by minus 1. 3, 2, 1, 0, 0. We have remove 3 and for values 1, 2, 2, 0, 0, 1, 0, and replace 2 minus 2, 0. 1, 0, 0, 0, 0 exists. J6, 6 plus 2, 24, even. Use Hakimi algorithm. Remove, and overall we have minus 1, therefore it not exist, and over 4, 3, 2, 2, 1, even. Use the same algorithm, replace, and minus by minus 1, and we got zeros because it exists.
So now let's start solving the third section, and in the first task we should find which of 10 pairs of graphs are isomorphic and which are not. So let's start with the first pair. First and second graph, they're not isomorphic as they have different number of edges. First and third graphs have the same amount of edges, 2 vertices with degree equal to 3 and 2 vertices with degree equal to 2. So as these conditions are satisfied, we now can try to relabel the second graph, and we can see that they're both isomorphic. As for example, vertex A has 3 edges and it's connected with D, B, and C, and here we have the same situation as with the other vertices. So first and fourth graph are not isomorphic, as again they have different amount of edges. First and fifth again satisfy the same conditions as the second pair, and now we can try to draw a second graph and relabel it, and again we see the same situation as we had here. So second and the third graph, they have different amount of edges, that's why they're not isomorphic. Second and fourth graphs, their vertices have different degrees, that's why they're not isomorphic. Second and fifth, again different number of edges, that's why not isomorphic. Third and fourth, they have vertices with different degrees, that's why they're not isomorphic. And then third and fifth, they're isomorphic, as again these two conditions are satisfied. And again, if we see our third graph and the fifth one, they have their vertices have the same amount of edges and they're connected to the same vertices, that's why they're isomorphic. The last pair, fourth and fifth graph, they're not isomorphic, as again their vertices have different degrees. So now let's continue solving the third section, and in the fourth task we again have 4 pairs of graphs, and we should define which of them are isomorphic, and if they are, we should draw the relabeled version of the graph. to prove that they are isomorphic. So the first pair of graphs is not isomorphic, as their vertices have different degrees, but in the B's part, we can see that these graphs are isomorphic, because if we draw both of them and try to relabel all vertices from the second graph, we can see that, for example, A's vertex have two edges and it's adjacent to Q and T, which equals to E and B, and the same situation with all other vertices. And here I also listed like a function that transforms vertices from the first graph to the vertices from the second graph. So again, in the C part, we have the same situation as in A, because these graphs are not isomorphic, because in the first graph, vertex B, which has a degree 3, is adjustment to one vertex with degree 1 and one vertex with degree 2, but vertex R with degree 3 is adjacent to two vertices of degree 2. That's why these graphs are not isomorphic. And in D part, these graphs again are isomorphic, and here we have the same solution as in B part, so I won't explain it for the second time. In the fifth task, in A part, we should say whether the drawn graph is isomorphic to K34, and it's not, as it has a vertex with degree of 5. And in B part, we again have another graph, and this graph is isomorphic to K44, and we can make two bipartition sets, A, B, C, D, and E, F, G, H. And for your convenience, I also draw this graph and listed all vertices.